What specific problem does the new method or algorithm aim to solve?
The new method, Mixture of Agents, MOA, aims to solve the problem of enhancing the generation quality of large language models, LLMs, by leveraging the collective expertise of multiple LLMs. The method addresses the inherent constraints on model size and training data faced by individual LLMs by introducing a collaborative framework where LLMs work together iteratively to refine and synthesize responses. MOA specifically aims to harness the collaborativeness of LLMs, where models tend to generate better quality responses when provided with outputs from other models, even if those outputs are of lower quality. By carefully selecting LLMs based on performance metrics and diversity considerations, MOA mitigates individual model deficiencies and enhances overall response quality through collaborative synthesis. The method is designed to improve reasoning and language generation capabilities by utilizing the strengths of multiple LLMs in a structured and iterative manner. Ultimately, MOA aims to achieve state-of-the-art performance on various benchmarks, showcasing significant improvements in response quality compared to individual LLMs.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method, Mixture of Agents, MOA, leverages multiple large language models, LLMs, to enhance response generation quality through collaboration. The process begins with LLMs in the first layer, independently generating responses to a given prompt. These responses are then passed to the next layer of agents for further refinement. This iterative refinement continues across several cycles until a robust and comprehensive response is obtained. The selection of LLMs for each MOA layer is crucial and guided by two primary criteria: performance metrics and diversity considerations. Models are chosen based on their demonstrated performance metrics and the diversity of their outputs to mitigate individual model deficiencies and enhance overall response quality through collaborative synthesis. The MOA framework aims to capitalize on the strengths of multiple LLMs to produce superior outcomes without the need for fine-tuning, solely relying on the prompting interface of the models. The structure of MOA consists of multiple layers, each containing a set of LLMs, where responses are synthesized through an aggregate and synthesize prompt. The final output is generated by an LLM from the last layer, ensuring effective collaboration among models and improved response quality. The MOA methodology draws inspiration from the Mixture of Experts (MO) approach in machine learning, extending the concept to operate at the model level by utilizing multiple full-fledged LLMs across different layers. By incorporating multiple LLMs in a collaborative manner, MOA enhances response generation capabilities and achieves state-of-the-art performance on benchmarks such as AlpacaVal 2.0, MTBench, and FLASK.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the Mixture of Agents (MOA) methodology outlined in the paper include 1. Enhanced response quality. By leveraging multiple large language models, LLMs, in a collaborative manner, the MOA methodology significantly improves the quality of generated responses. This is demonstrated through achieving a new state-of-the-art win rate on benchmarks like AlpacaVal 2.0, MTBench, and Flask 2. Collaborative synthesis. The MOA framework capitalizes on the collaborativeness of LLMs, where models generate better responses when exposed to outputs from other models. This collaborative synthesis leads to more robust and comprehensive responses. 3. Cost-effectiveness. The MOA Lite variant of the methodology emphasizes cost-effectiveness while still achieving competitive performance. It demonstrates that high-quality outputs can be obtained at a lower cost compared to traditional models like GPT-4 Turbo. 4. Diverse model capabilities. By incorporating diverse LLMs as proposers and aggregators in the MOA layers, the methodology can tap into the unique strengths of each model, leading to a more comprehensive and nuanced response generation process. 5. Scalability and flexibility. The MOA methodology is scalable and flexible, allowing it to be applied to the latest LLMs regardless of their size or architecture. This ensures that the approach can adapt to evolving models and technologies in the field of natural language processing. 6. Improved reasoning and language generation. The MOA framework is designed to enhance the reasoning and language generation capabilities of LLMs by leveraging the collective expertise of multiple models. This results in more coherent and contextually relevant responses. 7. State-of-the-art performance. Through extensive experiments and evaluations, the MOA methodology achieves top positions on benchmark leaderboards, surpassing previous best-performing models like GPT-4 This highlights the effectiveness of the approach in pushing the boundaries of LLM performance. 8. Efficient collaboration. The MOA methodology streamlines the collaboration process among LLMs by iteratively refining responses through multiple layers of models. This iterative refinement process ensures that the final output is a synthesis of the strengths of each model involved. 9. Specialization of models. The methodology allows for the identification of models that excel in specific roles, such as proposers and aggregators. This specialization ensures that each model contributes optimally to the collaborative synthesis process, leading to improved response quality. 10. Practical applicability. The MOA methodology offers a practical solution for leveraging the capabilities of multiple LLMs without the need for extensive retraining or fine-tuning. This makes it a viable and efficient approach for enhancing response generation in various natural language processing tasks.
How is the method validated or tested?
The method proposed in the paper is validated and tested through comprehensive evaluations using benchmarks such as AlpacaVal 2.0, MTBench, and FLASK. The results of these evaluations demonstrate substantial improvements with the mixture of agents (MOA) methodology, achieving a new state-of-the-art win rate of 65.8% on AlpacaVal 2.0, surpassing the previous best of 57.5% achieved by GPT-4 Omni. The validation process involves selecting models based on their performance metrics and diversity considerations to ensure higher quality outputs. The paper also compares the MOA approach with an LLM-based ranker, showing that MOA significantly outperforms the ranking approach, indicating sophisticated aggregation over all proposed generations. Additionally, experiments are conducted to analyze the impact of the number of proposers and model diversity on final output quality, showing that having a larger number of diverse LLM agents in each MOA layer improves performance. The method is further validated by comparing the responses of aggregators with proposers' responses using similarity scores, which confirm a positive correlation between win rate and textual similarity scores. Overall, the validation and testing process involve rigorous evaluations across multiple benchmarks and experiments to showcase the effectiveness and superiority of the mixture of agents methodology in enhancing language model performance.
What results were achieved with this new method?
The new method, mixture of agents, MOA, achieved significant results in improving response quality and performance of large language models, LLMs. Specifically, on the AlpacaVal 2.0 benchmark, MOA outperformed the previous best model, GPT-4 Omni, by achieving a new state-of-the-art win rate of 65.8% compared to 57.5% by GPT-4 Omni. Additionally, MOA Lite, a cost-effective variant of MOA, still outperformed GPT-4 Omni by 1.8%, achieving a win rate of 59.3%. The method also excelled in the MTBench and Flask benchmarks, showcasing its ability to push the boundaries further, even on already highly optimized tasks. In Flask, MOA demonstrated improvements in robustness, correctness, efficiency, factuality, common sense, insightfulness, and completeness compared to the single-model aggregator, Qwen 110B Chat, and even outperformed GPT-4 Omni in several key aspects. The method's effectiveness was further highlighted by its ability to leverage open-source models to their fullest potential, achieving top positions on various benchmarks and demonstrating a remarkable improvement over existing models.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the mixture of agents (MOA) method include the need for careful selection of large language models (LLMs) for each MOA layer based on performance metrics and diversity considerations. This selection process can be complex and time-consuming as it requires evaluating the capabilities of each model and ensuring they complement each other effectively. Additionally, the iterative refinement process in MOA may lead to increased computational costs and longer training times, especially when multiple cycles are required to obtain a robust and comprehensive response. Another limitation is the potential for diminishing returns as more LLMs are added to the MOA framework, as the marginal improvement in response quality may decrease with each additional model. Furthermore, the effectiveness of MOA heavily relies on the collaborativeness of LLMs, and if this phenomenon is not consistently observed across all models, it may impact the overall performance of the method. Lastly, the complexity of managing multiple LLMs in the MOA structure may introduce challenges in model coordination and integration, potentially leading to issues in response synthesis and coherence.